In the first revolution, the velocity vector goes faster than the acceleration vector, but by the moment in which it passes 3/4 of the first revolution, the acceleration vector takes off and seems to reach twice the amount that the velocity vector arrives, and both reach their maximum point and no longer continue to grow. That means that they stagnate. The first vector goes slightly faster than the friction vector, which is barely 0.1 seconds apart from each other, and both apply the same amount of force and friction all the time, so they are shown in the graph as straight lines. In the first graph, that is the graph of the force, it can be seen that the applied force is for 0.5 newtons, the net force is for 0.3 newtons, and the friction force is for minus 0.2 newtons. In the second graph, that is the graph of the force radius, it shows that the applied radius is 4 newtons, and in the same way the friction radius of 4 newtons. And finally, in the third graph, that is the graph of the torque, the applied torque is for 2 newtons, the friction torque is for minus 0.8 newtons, and the net torque is for 1.2 newtons. The values never change, so they always go in a straight line.
We can see that as we start, the velocity vector was the first to appear. Then the acceleration vector got larger than the velocity. The velocity of the torque changed drastically. In the first revolution it took 20 seconds, and the second one was just 7 seconds. In the first graph we can see the three go straight. The force applied was of 2 newtons, the friction was minus 0.8 newtons, and the net force was of 1.2 newtons. In the second graph we can see that the moment of inertia is the same in all the time, with 2 kilograms. And the third graph, this angular acceleration of the ladybug and the platform are both equal with 0.6